So, in this lecture, we will talk about the electric charge and magnetization distributions in nuclei. I will discuss how this is done using electron scattering and how one obtains information about these distributions. I will not discuss how matter distribution is inferred from other experiments, from hadron scattering experiments, but we will do so in a lecture in the future. In general, this is true of any probe. Uh, you want to look at some object, then the wavelength of the probe that you use has to be smaller than the size of the object that you want to probe. In the case of a nucleus, the size of the nucleus is of the order of a few Fermi, and if you have to probe it, the de Broglie wavelength of that probe should be less than r. So, for instance, for an electron, the energy should be at least about half a GeV. Okay. So, this just sets the scale of the energy that you have to use. If you remember, the Coulomb's elastic scattering cross section goes like Z1, Z2 for a charge of Z1e scattering off another charge of Z2e at a center of mass energy E, angle theta in the center of mass. Then this differential cross section goes like Z1, Z2 E squared, where E is the electronic charge, divided by 4 capital E squared, this whole term squared, divided by sine to the 4 theta by 2. And of course, if you put in some of these constants, you will get about 1.3 times Z1, Z2 by E, 1 by sine 4 theta by 2 in terms of millibarn per steradian. For an electron scattering of an extended charge, let us assume spin 0 for the target, then in the Born approximation, which is true for Z alpha, where Z is the charge of the nucleus and alpha is the electromagnetic coupling constant 1 by 137, the differential scattering cross section neglecting electron spin is just given by 4Z squared alpha squared H cross C E squared divided by Q C to the power of 4. This is for a point charge where so first we'll talk about what happens for a point charge, then we'll go to extended charge. So where P and P prime are the electron momenta, initial and final momenta, and E prime is the capital E prime is the final electron energy. So the momentum transfer, the vector is just given by P minus P prime, both being vector quantities P and P prime, and this is the momentum transfer. Now, if of course you have a distribution, then the angular distribution changes somewhat, and we'll come to that a little later. So the if you have a if you want to include relativity, then of course you get the so-called Mott cross section for an electron includes the spin effect. So the d sigma by d omega Mott is given by the Rutherford cross section, which is spin independent, times 1 minus beta sine squared theta by 2. Now, beta here is just the velocity of the electron by c. For a relativistic electron, beta is close to 1. So, this would just be like 1 minus sine squared theta by 2. Notice that you can cast it in a form where this is cosine squared theta by 2, and we will come to that what that affects in terms of the cross section for electron scattering. So, this additional factor comes about from the conservation of helicity, where helicity is defined as spin vector times dot product with the momentum divided by the magnitude of these. There is a typo there, there should be a bracket beyond P as well. So, let me just add it here. So, there should be. So, at theta equal to 180 degrees and for beta close to 1, d sigma by d omega Mott is almost 0. Okay. So, in fact, this will be the rationale for doing magnetization or magnetization distribution measurements at close to 180 degrees, electron scattering at 180 degrees, because the charge contribution to the scattering is close to 0. So, for a finite size of the nucleus, this experimental cross section d sigma by d omega is the Mott cross section times a f of q whole squared, where f of q is we have defined here above is the Fourier transform of the charge distribution of the electric charge distribution in a nucleus. Okay. For a spherically symmetric case, this f just depends on the magnitude of this vector. So, it just depends on r, and if you put in this, you will see that this f of q is just rho of r times sin q r by h cross by q r by h cross times, of course, r squared dr. If you do the inverse of that, then you can get the charge distribution from the way the f of q squared behaves. So, f of q squared is something that you can measure. You can measure a cross section and how it changes with the momentum transfer, and in principle you can get the, you do the inverse Fourier transform, you can get the charge distribution. In practice, of course, it requires a measurement of the cross section over a large range of q, and at high q, of course, the cross section drops, because that drops to like 1 by q to the 4. So, what you do, of course, is you assume a f of r, and then you calculate d sigma by d omega, and then compare it with experiment, and then iterate. So, you make a better approximation for f of r, and then I again calculate this, and so on. The first minimum of the f of q for a sharp cutoff radius r is when q modulus of the momentum transfer times r by h cross is of the order of 4.5. And in the limit that q is small, f of q is approximately just 1 minus a sixth of q squared times the mean square radius. Okay. So, of course, for s not equal to 0, there are additional terms present, and so from this you can actually get the mean square radius of the charge distribution in a nucleus. There was a parameterization which was done by Rosenbluth in 1950, where the d sigma d omega was put in a form d sigma by d omega mott times a g of e of q squared times a tau times g of m of q squared divided by a factor 1 plus tau plus 2 tau times magnetic, the same magnetic form factor times tan squared theta by 2. Now, you can see that when the mott cross section goes down to 0, this first part goes down to 0. However, the second term, if you remember, this mott cross section for beta close to 1 becomes actually cos squared theta by 2, and that cancels with the denominator in the tan squared theta by 2. So, you get a sin squared theta by 2, and that, of course, for 180 degrees is just 1. So, you are actually sensitive to the magnetization distribution. Okay. So, g of m of q squared, that is what you are sensitive to. Q squared, of course, is a 4 momentum transfer, q0 squared times minus q1, q2, q3 squared. Okay. Now, the g of e for q squared equal to 0 just becomes plus z. So, it gives you the sort of monopole charge of the nucleus in units of E. For q squared equal to 0, this becomes the magnetic moment of the nucleus in terms of the nuclear magneton mu n, which is defined in terms of EH cross and 2 mn c, where mn is the mass of the nucleon, the average mass of the nucleon. Okay. Now, in electron scattering, this is the general behavior of these cross section on a nucleus and on a nucleon. Proton is an example of a neutron, of a nucleon. So, you have the when you scatter an electron of the nucleus, then of course, you have a elastic peak, and then you have inelastically scattered electrons which actually excite low-lying states in the nucleus. And then you have a giant resonance where you have a collective behavior. You can have the giant E1 resonance, giant M1, E2, and so forth. And then you have a quasi-elastic peak where you have a electron scattering of a nucleon in the nucleus. Then you can excite the delta resonance. So, just as you can scatter quasi-elastically of a nucleon, you can also scatter off inelastically, and then you can excite the delta resonance, which is about 300 MeV above this one, and you can excite other resonances. This is the N star resonance, are again excited states of nucleon. And then if you go to still higher inelasticity, you can get the so-called deep inelastic scattering. For a proton, for instance, you have an elastic peak. Of course, the energy is corresponding to the elastic peak is different from the elastic peak that you get from a nucleon. So, this is of course a measure of the energy transfer, that means the energy loss of the electron going in this direction. So, if you have a electron scattering of a proton, then there is more loss, and therefore, you have this q squared by 2m. This is shifted from the elastic peak on a nucleus, where the nuclear recoil contributes only a very small amount to the energy loss of the electron. And then of course, you can excite the delta, N star and so on, and then similarly you can have deep inelastic scattering, where the electron is scattering off quarks in the nucleon. A typical electron scattering cross section, we have seen this already, that you have a d sigma by d omega versus angle for scattering of 40 calcium and 48 calcium. This is just to show that this is a schematic, and this is how it actually looks, the angular distribution for, let us say, scattering of calcium 40-48 nucleus in this region, elastic scattering, but as a function of q or angle. For electron scattering, since the Mott cross section is, this I have already said, but I will repeat it here. The Mott cross section is 1 minus beta squared and beta close to 1, then this becomes cosine squared theta, and then that is of course 0 for theta equal to 180 degrees, because cosine 90 is 0. So, the electric charge contribution is 0. However, the magnetic, as we saw, because of the extra term which is proportional to tan squared, then the cosine squared and cosine squared in the denominator cancel, and so you get a contribution only from the magnetic contribution. So, the magnetization distributions, if you want to have a handle on that, if you want to measure these, then you have to do these scattering experiments at backward angle, where the charge contribution, electric charge contribution is close to 0 or at least very small. And so, this is an example of a scattering measurement at close to 180 degrees, which is done by the spectrometer in Saclay. This is the reference for that. So, these are actually two spectrometers. So, this is a spectrometer that can actually go up and down. So, it will go in a plane which is perpendicular to the plane of the experiment of the ground. And this spectrometer of course can go from forward angle to backward angle, and so if you operate it at backward angle, then you can get this distribution. So, this is the transverse form factor, which is like the magnetization contribution as a function of the momentum transfer q, and you can see that this tells you about how the magnetization distribution is in a nucleus like 205 thallium, or it could be different in the case of 207 lead. And then these full lines and dashed lines are various calculations which single particle, or then there are higher order effects like the meson charge exchange current and so on. So, in any case, this gives you the magnetization distribution, which can be then compared with the theory. So, this is an example of another electron spectrometer, which is at the Mainz microtron called MAMI-B, and there are these three spectrometers, spectrometer A, B and C, and they actually look at the electrons which are scattered when the electron interacts with a target somewhere here, and then these are taken up in various spectrometers like this out of plane of the scattering, and then you can make measurements on these. So, for instance, from the MAMI machine, you can get a 820 MeV electron, and you can look at these electrons in any one of these spectrometers. Okay, as I said, you can do these experiments on a nucleus, on a nucleon as well. And for instance, if you looked at EP scattering and neutron electron scattering. You can take a neutron beam and scatter it off electrons the other way around, and do it at low momentum transfer. These are the references. You can get the root mean square charge radius on a proton to be this of the order of Fermi or so. There is some difference between the two measurements, and in fact, even now there is some discussion going on as to there are also measurements of this root mean square radius using mu-mesic atoms, and there are some differences there. That is, attempts are being made to resolve these differences. But the point here is that you can make such measurements and fairly accurate ones. For instance, this measurement is roughly 1 part in a thousand, okay, 1 per mil accuracy. Similarly, the root mean square or the mean square radius, charge radius for a neutron is minus 0.113 times plus minus 0.005. So, this is like a 5% accuracy result for a neutron. Notice that this mean square radius, charge radius is not 0, it is minus. And in fact, we will probably look at it in a subsequent slide. This can be understood within a sort of in a heuristic way if you consider the neutron to be actually making virtual transitions to a proton plus a pi minus. Then since the pi minus is lighter, it can go out to some distances, and the r squared is of course weighted by larger charge at larger distances, and therefore you can get a negative contribution to this r squared, the charge radius. Okay. So, in this slide we see from this reference Frua et al. And Fizerev letters in 77, the elastic scattering cross section of an electron on lead 208. Now, we will discuss this later when we discuss models, that there is something called closed shells. So, both the neutron and proton are closed shells. So, this is a nucleus that was attacked by this experiment, measured this cross section over several decades. By the way, you can notice that this cross section goes from about 10 to the minus 25 centimeters square per steradian to as low as 10 to the minus 38. So, this is like 13 orders of magnitude. So, this is really a fantastic experiment where you have measured the elastic scattering differential cross section d sigma by d omega over 13 orders of magnitude, and you see of course peaks and valleys in a smoothly falling cross section. And so, you can get very detailed measurements. So, you have measured it out to a Q's of about 4 Fermi inverse, and so therefore, you can get details of the inside of this electric charge distribution in lead 208. So, as I said, if you do the inverse Fourier transform, once you have a once you have the cross section as a function of Q squared, then you can invert that and get the charge rate, the electric charge density as a function of R, and this is what is plotted here. So, you see a Fermi-like distribution, a half radius which is at a little beyond 6 Fermi, and then there is, the statistics is so good that you can even discern a small dip in the charge distribution and then a rise at the center. And in fact, this is something that has to be understood within all nuclear models. Okay. So, such a charge distribution, of course, using this electron scattering out to fairly large momentum transfer has been measured, and you can see a series of measurements. This is summarized in this review article by Frua and Papanopoulos in the Annual Reviews of Nuclear and Particle Science 1987, and you can see what is plotted here is the charge distribution as a function of R for nuclei. Of course, a sample, there are many more nuclei for which this has been measured, but for the helium 4, which is just the alpha particle, carbon 12, oxygen 16, 40 calcium, 48 calcium, because 48 calcium, as we saw earlier, has a bigger neutron skin, 90 zirconium, and 208 lead. So, this is compared the experimental values that are inferred from this angular distribution up to fairly large q squared, the order of 3 to 4 Fermi inverse. That is compared with the mean field theory, and so this, you can see the agreement is reasonable for larger r, but not terribly good for smaller r. So, you have to tweak certain things, and so anyway, this tells you which direction you have to make improvements on the so-called mean field theory, where a nucleon is moving in the mean field of generated by all the other nucleons. Okay, so the charge density distribution rho of r, that can be parameterized in the form of rho 0 divided by 1 plus exponential r minus b by a. So, this is the so-called Fermi form factor, and the inference from these measurements, the value for b is about 1.1 times a to the 1/3. So, it increases, as you can see, this increases going to outer and outer r. So, this is this b, the half value charge density radius, and a is the so-called skin thickness. So, the skin thickness over which it falls from, let us say, 75% value to 25% value. This is of the order of 0.5 Fermi. Okay. This is a factor, the denominator of this r minus b. So, if the nucleus is approximated by a uniformly charged sphere of radius r, so you have basically a kind of step function. The density is constant over a up to a r, small r of equal to r. Then the r inferred is 1.2 times a to 1/3. This is so-called hard sphere approximation, and this implies, of course, that the saturation density in a nucleus is of the order of 0.17 nucleons per Fermi cubed. You can also look at the inelastically scattered electrons, and then you can infer about the excited states in a nucleus which couple to the electron. And for instance, if you do it at back angles, then it couples to states which are magnetic excited states, so such as M1, for example. Of course, it also couples to other states which is 2 plus and so on, 3 minus. And so, for instance, if you do it on carbon, then this is a spectrum taken from electron scattering experiment. Electron energy to start with is about 500 MeV. It can excite, of course, you can elastically scatter off the carbon nucleus, which is this peak. Then you can get the 4.44 MeV peak at which corresponds to the 2 plus state in carbon 12, the 7.65 MeV, the so-called Hoyle state, which we will have, of course, occasion to discuss later on. This is a 0 plus state in carbon 12. This is actually responsible for synthesizing elements like carbon 12 and beyond in the universe, and then the 9.64 state and so on, and higher excited. This is the 15.1 MeV state here that we discussed. This is the M1 state here, and so on. If you go to backward angles, of course, this will be more prominent than the other states like the 2 plus state and so on. This is another example of a elastically scattered state, 1 plus state in calcium 48 at 10.2 MeV, and this is the form factor squared plotted here as a function of the momentum transfer. So, you can see that it follows a general behavior, a diffractive kind of behavior, and this tells you about the magnetization distribution in this state in calcium 48. Sorry, this is from the reference given here, Richter in 2005. Okay, now this experiment, there is a very fine experiment done by Frua and his group in Saclay, where they measured the d sigma by d omega for elastically scattered electrons, again over several orders of magnitude, uh, in thallium 205 and lead 206. Now, the only difference between them, for instance, each of them has 124 neutrons. So, 205 thallium has 124 neutrons and 81 protons, whereas 206 lead has 124 neutrons, but 82 protons. So, this the thallium nucleus as a whole in the last level, the shell model state, and so there is just a difference of 1 proton between the two. So, the ratio of these two, thallium 205 to 206, as a function of Q was plotted here in this paper, Cavadon et al. 1982 paper, and you can see that this oscillates, and it has a peak at about 2 Fermi, and then of course, it again goes down. So, the difference between the charge densities is what is plotted here, and this shows a peak at r equal to 0, which means that this is coming from an S configuration, S state, and then it goes through a minimum and then through a much smaller maximum and so on. So, the full line shows the mean field calculation, and the dashed line is is what you get if you have a 70% reduction in that in the last orbital, which happens to be a proton in the 3s half state, the shell model state. Okay, so, this gives you somewhat better agreement. Okay. So, even such precise information about the difference due to just a single proton can actually be measured by such electron scattering experiments. They are not, of course, very easy measurements, but they can be done, and the good thing is that you can actually pin down the charge density due to just a single proton, single odd proton, by doing such difference experiments. Okay. So, in summary, we have seen how electron scattering can be used to probe electric and magnetization distributions. I mean, the form factors is a function of momentum transfer, and then of course, if you do a Fourier transform, you can get the distributions in space, the radial distributions, for example. We have also seen how precise data can give information on the form factor of a single particle in the nucleus. Okay. This example was taken from literature. This experiment actually has been done more than 40 years ago. The difference in scattering cross section between 206 lead and 205. I thought I should show this because it just shows the kind of beautiful results that you can get by doing such electron scattering experiments. Okay. Thank you.